I'm the Vice President and General Manager for Open Ecosystem team at Intel. Today, I'm very happy to be here with Tony. Hi, Tony.
Hey, here.
Excellent. Yeah, my team is Open Ecosystem. You can learn all about us at open.intel.com, or you can catch us at a beautiful podcast on open.intel.com/podcast. Tony and I are going to be talk about something which is pretty hot in the industry these days, LLMs, and how you can get a huge performance gain and boost by running inference on these LLMs on AWS instances. So, Tony, do you want to give an introduction to yourself?
Absolutely. Hey, everyone. My name is Anthony Vance. Um, I'm an AI software architect in our data center and AI group, and I've been working mainly on software optimizations for LLMs in the last few months.
Wonderful. And what are we talking about today?
So we are talking about how to deploy LLMs in AWS instances, AWS m7i instances specifically, and so we have some data points to showcase that how to achieve a lower latency for your LLM models, and also we have a nice demo which was recorded running in AWS to showcase that how you can host a latency sensitive application like chatbot, and we'll also learn about how the m7i instances comes with AI accelerated compute, right? Like an advanced matrix extensions, which is kind of baked into each and every core of m7i instances.
So, having a low latency is super important in an LLM, particularly if you are doing in a chatbot style interaction, because I don't want to be typing my message and waiting for a few seconds, forget about minutes, for the response to come back. So, we're really looking at sub-second response back so that you can truly have that interactive chat.
That is true. That is exactly true. You know, usually about humans can interact about the maximum 350 words per minute, right? That kind of translate into 100 milliseconds. Then, so when you're running LLM, you should be able to return your words, at least within 100 millisecond, right? And that's what we will also see today, that some of the model hosted in m7i, what's the latency you're getting it back.
I just pause for 2 seconds just to give people a feel that what does a 2 second latency look like? It's like, are you saying something? Are you stuck?
that's
Or what's going on?
that's a nice trick, yeah.
Right? Well, people should get a feel for what does a second or two look like in terms of this latency. All right, Tony, I know you have some excellent content here. I'm really excited. Let's jump into it.
Oh, excellent. Okay. I just wanted to start it out with, since we are talking about m7i instances, I just wanted to mention that the Intel 4th Gen is, Xeon, which is codenamed as Sapphire Rapids, right? Which is in AWS now, and it is launched as m7i and as well as c7i instances. m7i is a general purpose instance, and c7i is a compute optimized instances, right? That's all I wanted to mention today. And throughout our talk, we will talk more about the m7i instances, but the similar the performance, you can also achieve in c7i instances, but we will go deeper into m7i instances today.
So this is a seventh generation instance on AWS that is based upon the fourth gen Xeon instances. So AWS customers are used to the M7i, C7i, but just to help them understand, this is the fourth gen Xeon. That's what it is based upon.
You're exactly correct. Yes, most of the customers are used to their sixth generation, which is like m6i, c6i instances, right? I think this will give a good idea about if you are deploying in either or even m5, right? What performance you can get with m7i and what are the differences between those two instances.
Okay.
Sounds good. So since we are talking about AI, so I wanted to bring up the fundamental differences between your previous, the sixth generation of AWS instances and the seventh generation of the AWS instances. So in M6i, what we have called AVX 512, it's a vector-based accelerations, and you could do integer 8 operations in that instruction set itself. Then we have introduced what we call deep learning boost, and it's also referred as VNNI, that kind of increased your operations per second by 3 times. Now, the m7i instances comes with what we call advanced matrix extensions, and as part of it, in each and every core, what we have is a 2D registers, and also what we call tiled multiplication engine, what we call TMUL, and that kind of accelerates our AI matrix multiplications by 8 times better than m6i. So I wanted to point out that with this you have enough scalar and vector matrix extensions on a single chip, right? And the another critical part is that all of these the hardware features are already baked into our software ecosystem. For example, if you're using PyTorch, you don't have to do anything to make use of the AMX, right? You deploy a PyTorch code, if you choose either integer 8, or if you're using a bfloat 16, then it automatically, those kernels gets deployed into AMX. So it just comes as part of the CPUs. The software ecosystem is also enabled to make use of these hardware features.
So these are called as accelerators. So AMX is an accelerator, but it's just a part of the integrated CPU itself. So if you're using M7i, the AMX accelerator is enabled for you by AWS. And so from your perspective, you're just using the PyTorch code, and you just use the natural data types that are part of PyTorch. And
Yes.
we have done the optimization to PyTorch, which automatically offloads this from the main CPU to the AMX accelerator and do this in a faster way. And as you said rightly, from M6i to M7i is 8x better performance.
Yes, 8x. From a pure compute perspective, it is. You have a 8x higher capacity. Which is in the M7i instances. That's correct. Yes. Then I also agree with all the most of the folks don't know that Intel is a hardware company, but Intel makes huge investments. You are the advocate for it. Huge investment in software, right? And similarly, there is a lot of investment Intel is making in PyTorch, and that's been showing up here. Yeah.
Well, I mean, we have over 19,000 software engineers, first of all. We have
Yeah.
lots and lots of those engineers really contributing to 300 plus open source projects. And last week we did exactly a seminar on this with Fan Zhao. We talked about exactly about PyTorch, that
Oh,
why do
nice,
we
nice.
contribute to PyTorch and how those optimizations are available on M7i directly itself. And really, I think you're touching on a very important point here. The reason Intel contributes to these open source projects is because our customers who used us in CSPs, data centers, networking, edge devices, they expect these open source projects to be fully optimized so that they use those languages, those design patterns that they're used to, and get the optimal performance out of it out of the box.
Exactly. Yeah. Well put.
Beautiful. Okay, let's keep going then.
Okay, so since we are talking about large language model, I have a few things to talk about. Give a basic about large language model, right? And we could also map into some of the data which we are going to see. So if you take a step back, we are saying large language model, but that is one part of a generative AI model for a text. So it means that when you are invoking a model, it's going to generate one word, or what we call one token. But underneath, the model responds differently to the hardware. For example, let's say you take a model called Llama 7 billion parameter model, right? And you're giving a page of text, which can be 2,000 words or 2,000 tokens, and you're asking it to generate some text to either you're asking a question or you're asking a model to generate next set of words. What happens is that it goes through a complete model execution, then it generates one word, and then you have to feed that word back again to generate the next words. So the first word generation, it behaves differently because when you're generating the first word, you have to process all the words coming in, and you're creating a context, and that context is what kind of saved as a key and value cache as a data structure inside our execution environment, right? So your first token, usually it's very compute intensive. Now when you feed back the word and you're generating, the second word, right? And then it just goes into the loop for generating all the multiple words. Now, from the second word onwards, what happens is that it's making use of the computer, the cache, so it becomes a memory bandwidth intensive, right? So for the compute intensive task, the Intel AMX helps. Similarly, even for the memory bandwidth intensive, since we bringing in the data type to bfloat 16 and integer array, and also m7i instances kind of comes with DDR5, then we reduce the decoding latency in that way. So I just wanted to, it's very interesting, because what we see mainly in LLM model, right? So the LLM model kind of applies both pressure, the compute pressure and as well as memory bandwidth pressure, right? I think we'll see some of the data to see how m7i handles both.
Yeah, that's how I was processing the information as well, because there is compute happening in terms of constantly feeding that word back and the next word back and the next word back. And then there is memory on how many words you can take in and then be able to generate that predictive text according to that. So I think what you're telling me is M7i using AMX extensions or AMX accelerator really offloads those two capabilities to AMX and then allows you to bump up that. That's really the main reason why 8x performance boost is happening.
That's correct. Yes.
And maybe another point to note is that 8x performance boost is what we have seen in our experiments, in the research that we have done. But customers would definitely want to try this in their own setup. The numbers could vary.
Exactly. So the 8x is the absolute, the absolute the compute capacity what we have. We'll also see some data points where how much the cost savings they'll get, actual word, right? What we typically see is that I'm just giving a sneak peek. We do have data points, right? When you're running a really large model, the numbers usually reduces, and when you're running a little smaller models, right? What happens is that if I go into a little more technical details, right? When you're running a smaller model, the model can stay in your cache, then you're just maximizing the AMX, right? So then you will really see anywhere between 6x to 8x performance improvement. But when you go for a larger model, that will reduce a little bit because of your memory bandwidth pressure also comes in there.
Yeah, so as you said, rightly, there's a compute pressure, there's a memory pressure, depending upon what kind of model it is, what are you truly offloading, and how much you're able to repurpose. You will see the benchmark numbers varying.
That's correct. Yes.
Okay.
Yes. But one of the important things is that the data type, the bfloat 16 data type, which is enabled because of AMX, right? That adds a lot of value here, to reduce the memory bandwidth pressure.
Got it. Understood. Okay.
Excellent. So now that we talked about what are we doing in AMX, this is just one data point. Let me explain what's going on here. So we have this chart where what we've done is that we moved a model, which is Llama, to 7 billion parameter model, right? This is in the lower to medium spectrum of your large language model. And it was running on FP32 in our m6i instances. Now we moved that into m7i, and we converted into a bfloat 16. Now when you do that, we see about the cost savings of 2.5x cost savings. When you're moving a model from m6i to m7i. And what we've done is that we also moved a model which is running on with intake precision. Then we moved into m7i, and that gave about 1.4x cost savings, right? And these cost savings are kind of derived from our throughput, and there is some data point for you to refer that how these costs are calculated. So while we are talking the Llama 7 billion parameter model, right? What I wanted to highlight that the smaller spectrum, the smaller spectrum of large language model important roles in the industry, right? That there's a huge wave for really large models, like a trillion parameters or 200 billion parameters model. But what we see is that in a typical enterprise deployments, right, the smaller models are good enough for the accuracy. You can get a same accuracy of ChatGPT for your own data set, right? You don't need a ChatGPT level model, to run at your place to provide the same accuracy, because you have your own data, and as long as your accuracy is good enough for the data, you can deploy the smaller model. That's why we just picked up a smaller, the small set of model to showcase that you could run this very well in our Xeon instances, the m7i instances, and you could save the cost by moving those models.
So while there may be usages for larger models, but what you're saying is a lot more usages are going to be around smaller models. And so essentially this cost saving by moving to bfloat 16 or just int 8, from m6i to m7i is going to show you good price saving right there.
That is correct. That is correct. You're right. Yes, exactly. Yeah.
Okay.
Now, if you go a little deeper into, this is where, I want to tie it up with the initial, the latency talk, we were having. So this is a little more raw data. Right? What we've done here is that we've taken a public Llama 2 model, which is open source by Meta. Then we have benchmarked that in m7i instances. There are 2 instances we have chosen, 8x large, which will have a 16 cores, and 16 physical core and 32 virtual CPU. Then 16x large, which has a 64 virtual CPU. The right side, what you see, what we call the decoding latency, and the left side, which is called the compute, so the prefill latency, or the first token latency, right? And we also compared with the different token sizes, right? The 256 and 1024 are the number of tokens you're feeding in. Then what's the latency you're getting, right? So I want you, focus your eye on the right side, because the second token or the decoder latency is the important one, because that's where you're generating a lot of tokens, right? Let's say if you're generating 1,000 tokens, that's going to take majority of your latency, right? So when you're running an m6i, m7i 16x large, you are getting less than 50 millisecond latency. But even with a smaller instance like 8x large, it's around 50 millisecond latency, right? And these latencies are good enough for your latency sensitive applications, right? I'm just going back to my comment about how what is the words per minute the human can interpret, right? And that also defines your human interactive applications, right? It can be chatbot, or it can be coding assistance, right? Where you're writing a code, you're predicting the next your code snippet. So just wanted to highlight that these latencies are good enough by hosting them in m7i instances, and these are all some of the raw data.
And so when you're saying 1,000 tokens per minute, that's basically each token is a word essentially, right? Like
So
when I ask a question in Chat GPT and it's spitting out words, each word is considered as a token output.
That is correct. Yes.
Okay.
Yes. So as a thumb rule, you can say that each token is like 0.75 word.
And why do we call it as a 0.75 word?
So, so when you're generating a word, let's say you're generating a the, then there is a comma come in. The comma could also be a token. So you're not comprehended, but you anyway you're going to predict it. That's why if you are converting a tokens to a the word which you can comprehend, then it reduces, right? But there are folks. It depends on how they generate a token. It's funny. We were talking to our friends in China, where they said that we were saying that in English you need to predict a lot of tokens, and they just said that no, in China, in our language we just predict very small set of tokens, because then each word conveys a larger set of message. Like, I'm not very well versed in Mandarin, but that was a pretty nice insights I got. Yeah.
Yeah, no, I think that's fantastic, because I've traveled to all sorts of countries around the world, and usually when you go, they will tell you that, Arun, like if you are, I think Brazil is where they said, oh, whatever you're saying in English, I'm going to take 30% more words to explain that in Portuguese. So I think it was Brazil. So essentially, the point is the expression in each language is unique. And so far we have seen that problem only in humans, but ChatGPT only exemplifies that problem to at a bigger scale.
That's
And
right.
it's not a problem, it's just what the language is.
That's right. Yeah. It's different, yeah. different language, different things. So it depends on how, it also based on, data scientists and algorithm engineers, right? How they view as a token. I also seen that, you could make each word as a token or a group of sentences as a token too, right? So then you generate them very fast. So it depends on how you design how you architect your models.
Yeah, so basically, depending upon your model, you could be you are defining what a token is. Token could be a sentence.
Yes.
Maybe you're doing a lot of the processing in the model, or maybe
That's
you're
correct.
spitting out a, as you said, comma, full stop, period. All that punctuation could be a token. So the granularity is upon the model owner.
That's correct.
Okay.
That's correct. It depends on how you train it. Yeah.
Okay.
So I want to extend it, go to the next size model, right? 13 billion parameter. And 13 billion is also important thing because in many benchmarks, what you've seen is that 13 billion could match ChatGPT kind of accuracy for a specific data sets, not the broad data set, right? Just going back to the fact that ChatGPT is great for generalized, you can ask any questions. But when somebody deploys a particular model, they don't want the model to, question like Wikipedia. They just want the model to answer their own policy documents, their own legal documents, right? So what I wanted to highlight is that the first token is still under, 1 second for most of the scenarios. And the second token is, under 100 millisecond for an instance size like 16x large, which uses 64 vCPU, right? So if you're using a 13 billion parameter model, and if you're using, still you can host a latency sensitive applications, which is less than 100 milliseconds, right? That's another addition, and which is enabled by AMX and as well as the memory bandwidth advantage we have in m7i instances.
So the 50 millisecond would be really good for a chatbot kind of an application. What's the typical use case for a 100 millisecond model?
So what I would say that for a chatbot kind of applications, right, I would say is I think the 100 millisecond is good enough, right? But the 50 millisecond it's kind of a preferred, and it enables some of the low latency applications. For example, it's possible that you might want to have a voice assistant also, right? Then you would want to have a little more lower latency, right? Or it's not just you're deploying LLM alone, right? You might want to do, let's say, an information retrieval pipeline before LLM, right? Then you want to budget some latency for that, right? Then the 50 millisecond makes sense, right? But if you're just deploying just a chatbot, which you already fine-tuned it, then 100 millisecond is good enough.
Got it. Okay, understood. No, that's fantastic, actually. Just for contrast, like when we look at ChatGPT, what is how many number of parameters it has been trained with?
So the ChatGPT, so that's been a secret with OpenAI. So we don't quite sure.
We forgot about that part.
Exactly.
OpenAI only has open in name, but otherwise it's a fully closed system.
That's true. So they have not disclosed the exact number of sizes, but there has been a speculation. We don't want to speculate that.
No, of course, no speculation here, but just the fact we know the fact that OpenAI is as closed as it could be. So
that's true. Yeah.
All right, cool. What else we got?
So I do want to just close this with a slide about the AMX aspect and how it enables the cost of inference, right? So I have a use case where we picked up a same 7 billion parameter model, and if you, let's say, deployed it, there is a way you could batch all your queries, then send it as a batch, right? And that's where the AMX excels. So it adds about 26% of latency for this specific use case, and it provides about 6x throughput, right? Because AMX is something which is a matrix multiply acceleration, right? The more data you pump in, it's going to give you a higher throughput, right? That's all it is showing here. So if you are deploying AMX, we would highly recommend to figure out how you can batch your queries so you can get the maximum out of m7i instances.
And that you are recommending is anyway a good practice. Like instead of sending one query
Exactly.
at a time. So this is nothing that AMX requires you to do, but it can further reduce your cost by following those good design patterns.
That is correct. Exactly. That's a good point.
Okay.
Yes. So I do have one simple demo where we developed a chatbot with Llama 7 billion chat model, which is hosted in 16x large instances. And we have another instances, where we're running GUI, right? And it just sends a request, and then you will see that, well, how quick, you're getting a token spec, how responsive it is, right? But I do want to mention that this is a recorded demo, but if you want to recreate this demo, we are given a link for the slides. So while the demo is playing, right? So this is pretty similar to what you see in any chatbot applications, right? There are a few things I want you to just focus on. The first thing is that the minute you enter a query, right, the query goes back and our backend, and you can see that we are asking a question about, can you write a Python code for standard deviation, and you can see that how responsive it is, right? And this is the model running on a 16x large with 7 billion parameter model, right? And also, even though it is 7 billion parameter model, it still can answer a different variety of questions. I'm just asking to write a code, then I'm just going to ask a question about, give me an itinerary for my New York visits, right? I do want to highlight that I'm not verified the the New York itinerary, but it looks good. So
Well, it's got Empire State Building, it's got Ellis Island, it's got Central Park, Manhattan. I think it's covering most
yeah,
of the points.
yeah. So yeah, I think that's all I wanted to showcase from a demo perspective. If you have if you want to play with it, they can always go back and refer this kind of demo from Intel.
And so in the webinar link on the LinkedIn post, we will actually post a link to the GitHub repo where they can
Absolutely.
reproduce this demo.
Absolutely, yes.
Okay, all right.
Okay, so we have we went through most of the the topic about the performance, AMX and m7i instances. So I do want to touch upon that the software stack it's being used, right? So that when you are going and deploy, you can go and look for these things. The primary software stack is PyTorch. A lot of optimization is going to upstream to the PyTorch, and that has been helped with what we call Intel extension for PyTorch, which is providing kind of extreme performance on top of PyTorch, right? For LLMs, a lot of optimization, we have pushed into Intel extension for PyTorch. Will make into PyTorch. So I will highly recommend to take a PyTorch and Intel extensions for PyTorch. Then here's the interesting things, which you have not covered. Maybe it's for another talk. Is the deep speed. With deep speed, you could split your model across multiple sockets. For example, if you're taking the larger instance in m7i, which is 48XL, and you could split your model and run much bigger model, right? Or reduce the latency further down, right? That's something we could cover in different talk. And all the models are used from the Habana, the Hugging Face repository. Then we have a tools, Intel Neural Compressor, Intel Transformer Extensions. These kind of helps the software stack, right? And these links, we'll paste it here. There are a couple of links. One is if you want to build a demo, or if you want to play with a neural chat, right? We'll give a link for that. Then also, if you want to optimize your existing models, or if you want to deploy those models, we'll highly recommend to start with this PyTorch, our LLM, which is open source code, which also provides kind of out-of-box examples for you to quickly run in AWS and see your performance yourself.
That's wonderful. And this, just to kind of highlight this Intel extensions for PyTorch, they're 100% open source. They're out there. Customers can use it. It is only a sort of an interim staging area until they make their way into PyTorch upstream, the main branch, essentially.
That is correct. Yes.
Okay.
Yes.
Beautiful.
Yeah. The LLM has been a really, we are all just printing, right? With catching up, right? So it is important that we also sprint along and make sure that the software optimizations are out there, for customers to use, right? That's why the Intel extension for PyTorch helps there.
Got it. Understood. Okay.
All right. So that's my last message, right? Before for this talk. Right, I want to highlight just these 4 messages, right? The m7i instances, they are accelerated by our infused instruction set, right? In every core, right? You don't have to do anything. It just comes with a m7i instances and as well as the software stack, right? And these instances, deliver, you've seen that, you deliver latency less than 50 milliseconds for, the smaller to medium size of models. And if you are in m6i, by moving to m7i, you're going to save costs up to 2.5x. Then just going back to and just emphasizing the same thing, we were talking about, right? We recommend to use Intel PyTorch extensions along with PyTorch, for LLM, to get the higher performance and as well as to save cost with the m7i instances.
So what you're telling me is I get better performance, lower cost if I'm using this PyTorch and extensions together on M7i.
That's
And
correct.
this will help you build a model faster. You can do the inference faster. So while there are a lot of training that is happening, but a large majority of it is actually inference. So in
That's
that
correct.
sense, definitely recommend people to check it out.
Exactly.
Awesome.
Yes.
Tony, is there anything else that I should have asked that I didn't ask?
No, I think yeah, it was very good. I think you covered all the topic. You asked the right question. I really like the way you paused for 2 seconds. I was not sure what is going on. Did I lose you or not? Yeah, it was a nice trick.
Well, sometimes those, just give people a dramatic effect that, "Oh, what does it mean? Like 2 seconds is a lot of time. So you want to get under 50 milliseconds of, latency? We got it.
Yep.
Awesome. Tony, thank you so much. I really enjoyed. And let me get rid of the slides first. And once again, thank you so much. Hope everybody really enjoyed the webinar as well. We have a couple of more webinars lined up in this series where we're going to talk about deep dive into M7i instances and all the fun things that we have been doing in the upstream community and how they are now available in M7i. So look forward to see you in another webinar soon. Thank you.
All right. Thank you, Aaron. Thanks
Bye,
for
everybody.
thanks for hosting me. Thank you. Bye.